Le cloud, ça, tu perds du, tu perds du truc.
C'est parti.
Mon écran.
Super.
Ok, j'y vais, Pierre-Yves.
Ben, écoute, ouais, on a le plaisir d'accueillir Arthur, hein, qu'on ne présente plus là aux orateurs qui sont présents. Allez, vas-y, Arthur.
So if it's okay with everyone, I'm going to do my presentation in English, just so people who don't speak French can also watch it. So today I'm going to present the work I've been doing towards a multi-model cardiovascular simulation framework. And today I'm going to focus on one-dimensional and three-dimensional models. So to put things into context, cardiovascular diseases are the leading cause of death worldwide. And this graph may have been shifted due to COVID, but I'm sure that cardiovascular disease still represents a large part of the deaths in the world today. And the reason for that is that, like cancer, for example, cardiovascular disease are often asymptomatic diseases that are difficult to diagnose, which means that they are usually detected too late and that the patient who undergoes surgery has lower chances of success and surviving. So just to give you an example, here on the two pictures that I've included in this slide, you can see two different responses to a similar...
Excuse-moi, Arthur. Je crois que ton écran, moi je vois pas ton écran. Là.
Ah.
Je pense que t'es pas sur le bon au niveau du...
Ok, attends. Et là, tu vois mon écran?
Ben, je sais pas, moi je vois...
On voit son écran, mais il n'est pas en plein écran, on voit une partie.
Oui. C'est pas en présentation, okay.
Là. Alors attends, peut-être qu'il faut que je partage tout mon...
Ah,
c'était mieux là.
Oui, mais...
Et là?
Ah, voilà.
Oh,
c'est bon, voilà.
Ok.
Ouais.
Ok, là vous voyez tout mon écran?
Ouais.
Ok.
Ouais.
So as I was saying, cardiovascular disease are often asymptomatic and difficult to diagnose. And as an example, you can see here two different responses to a similar pathology. So here, both of these patients have an occluding pathology here in one of their arteries. And you can see that the patient on the left, because of the pathology, has no blood flow going to his lower limbs, and therefore is in risk of ischemia, which is a low blood flow in his leg. Whereas the patient on the right here has a similar occluding pathology, but you see that there's a compensation mechanism that is triggered where some collateral vessels are being selected in order to compensate for the lack of blood flow going through the stenosed or occluded vessel and bring the flow to the leg by collateral vessels. So in order to understand why these how different patients respond to similar pathology, it's necessary to understand how blood flows in the cardiovascular system. So every cardiac cycle, the heart ejects a certain amount of blood into the cardiovascular system, and the shape of that, the flow rate that is ejected by the heart is similar to a half a sine wave. And if you measure every cardiac cycle, how the resulting pressure wave, for example, here in the right arm, you can see that the wave morphology is very different. And this from the wave morphology ejected by the heart. And this wave morphology is also going to vary from patient to patient. And the reason for that is that as the wave propagates in the cardiovascular network, and the wave, because the blood is incompressible, the wave propagates by deforming the arterial wall, which is an elastic material. As it propagates, it gets reflected in transmission at each bifurcation of the cardiovascular network, and therefore the wave morphology measured in each patient is going to be different as each patient has a different cardiovascular network. And so the question here is that we are going to ask ourselves is, based on this measurement that we can do very locally and very punctually, can we go beyond just monitoring heart rate, and can we infer more information on the patient's health? And so before doing that, we have to understand how the wave morphology evolves depending on the location in the cardiovascular network. So in this next slide, I'm going to look at how the pressure wave evolves as we propagate along the cardiovascular network. So close to the heart in the aorta, you can see that the mean value of pressure is relatively high, and that the amplitude of the pressure oscillations are large compared to the mean value, which means that the flow is pulsatile and inertial in these large vessels. So these vessels are organized in a network, as most of you may know.
Portion of red blood cells in for the same.
Okay. And was that a question?
Go on.
Okay. And so these large arteries are organized in a network where usually one parent artery gives rise to two daughter arteries. So as you move along the network, you reach smaller and smaller arteries, and you see that because these smaller arteries have a smaller radius, they become more resistive, and the amplitude of the pressure oscillation decrease compared to the mean value, and so does the mean value of pressure. And then you eventually reach the capillaries, where the arteries are, the vessels are no longer organized in a network, but are organized in what you can describe as a space-filling mesh. So typically, instead of being a parent artery gives rise to two daughter arteries, the vessels, the capillaries are tree-connected and form a mesh. And you see that at the capillary level, the flow is no longer unsteady. You can assume that it's steady, and the pressure is pretty low. And this is the natural response of the cardiovascular system in order to optimize oxygen and nutrient exchange at the capillary level. So this whole network of arteries, the goal is to transform the pulsatile signal that is ejected by the heart into a steady signal with low pressure in order to optimize oxygen and nutrient transport. So in order to help clinicians better understand the pathogenesis of cardiovascular diseases and be able to better predict the health of the patient based on punctual measurements, it's necessary to be able to model blood flow. So in order, and you have to model blood flow at all the scales I presented before. And so to do that, you have to understand that the cardiovascular system is a closed loop circuit. So typically, if we wanted to model the blood flow in the cardiovascular system, we would have to account for the pulmonary circulation, the mechanics of the heart, and then the arterial and venal circulation. However, because this is just too wide to be able to solve accurately, we focus here only on the arterial circulation. So we use boundary conditions to model the behavior of the heart and the behaviors of the other part of the cardiovascular system circulation. So namely the blood flow circulation in the veins and in the pulmonary system. And we assume that blood is an incompressible fluid, which can be Newtonian or non-Newtonian. So typically close to the heart in the large artery, the blood flow is a Newtonian fluid. But as you move down the network and you reach smaller vessel, because the size of red blood cells becomes almost the size of the vessels, you can no longer assume that blood is Newtonian, and you have to account for non-Newtonian effects. And on top of the fluid equations, you have to include a model for the deformation of the wall, because remember that because blood is incompressible, the way the wave propagates is through the deformation of the arterial wall all along the network. So here the focus on my presentation is going to be to build a multi-model framework. And the idea behind this multi-model approach is that depending on the region you're in the cardiovascular system, you do not need to always solve the 3D Navi-Stokes equations. Because you can see that, for example, in the capillaries, solving the 3D Navi-Stokes equation on a large scale first of all, it's probably impossible because of the number of capillary vessels, and also unnecessary because here the flow is steady, and you can actually solve it with simpler models. So typically, what I would call a zero-dimensional model, which are basically an electric analog to where you use an electric analogy where resistance is characterized as the viscous effects, compliance characterizes the elastic effects. You can also model those using a porous media approach, because since capillaries are no longer a network but a space-filling mesh, you can use homogenization technique to compute the equivalent porous media properties of a capillary mesh. But today I'm not going to talk about the 0D or 1D approach, and I'm more going to focus on the 1D and 3D approach, which we use to model the regions of the cardiovascular network where the flow is still has still some inertia and some pulsatility. So in the first part of my presentation, I'm going to talk about 1D model, and then in the second part, I'm going to talk about our current efforts to solve the 3D Navi-Stokes equation. So this is a work I have done during my PhD with Pierre-Yves Lagré and José María Fulana, and it's also in collaboration with people from Argentina, Japan, and two clinicians from l'Hôpital de la Pitié-Salpêtrière in Paris. So how do we derive a one-dimensional model? So this is a slice of what a large artery looks like. So you see that the wall of the artery is actually quite complex. It has several layers, and this is a typical geometry of a bifurcation. So you see here that the geometry is relatively complex, but in the framework of one-dimensional model, we only want to focus on capturing the wave propagation. And to do that, we can use simplifying assumptions. And the first simplifying assumption we use is that we consider that the arteries are thin axisymmetric cylinders. So for what this translates into for the wall is that the wall is now just a thin cylinder, and that the arteries are just straight vessel that of course can deform, because again, we want to capture wave propagation through wall deformation, but essentially they are straight when they're at rest. So now I'm going to focus on how we can derive a wall model using this first simplifying assumption. And so because the wall is thin with respect to its radius, when you balance the pressure stress with the stresses in the wall, you can derive what we call the Laplace Law, which is just the balance of the pressure and the azimuthal stresses in the wall. And if you assume that the wall is a homogeneous Hookean material, you can derive this elastic law, which relates the pressure jump from inside to the outside of the wall to K, which is proportional to the Young modulus of your material and the variation of radius, where R0 is the radius at rest. And so if we just use an elastic law, we've compared our results using an elastic law with experimental results given to us by our collaborators in Argentina. And you see that you're able to obtain the correct variation of pressure for the corresponding variation of radius, but you're not able to obtain the hysteresis loop in the response of the pressure response when you vary the radius. So we then included a second term, which was a viscoelastic term. And we see that now we have a bigger hysteresis loop. We have a hysteresis loop in the pressure response to radius variation, but this was not sufficient. And we eventually saw that we needed to add a nonlinear viscoelastic term in order to actually accurately capture the experimental results. However, if you notice here that the radius variation in this experiment done by our collaborators in Argentina, the radius variation is large, which is typically not the case in arteries. So in the following, I will neglect this nonlinear elastic term because it's a second order or third order term when we consider normal conditions in artery where the radius variation is very small. So now we were able to obtain a wall model, a viscoelastic wall model. So now we have to do the same and for the equations for blood flow, the fluid equation. And we simplify the Navier-Stokes equation by noticing that the wavelength of the pressure pulse that is propagating into the system is much larger than the radius of the arteries. And so using this assumption, we can introduce a small parameter in the incompressible Navier-Stokes equation and obtain what we call are called the reduced Navier-Stokes-Pront equations. And then this is still a 2D set of equations. So to obtain the 1D set of equation we're interested in, we average these equations over the cross-sectional area of the artery. And this is an exact averaging process, which introduces two parameters that are a priori unknown. First is the nonlinear parameter, and the second is the viscous parameter. And both of these depend on the shape of the velocity profile in the artery, because in the averaging process, we of course lose information about the shape of the velocity profile. So when we're solving the fluid equation, the 1D fluid equation, we have to give an estimation of these two parameters. So typically we set this quantity to 1 because its range of variation is from 1 to 4 divided by 3. So we can approximate this parameter to 1. However, this one can have a large rate of a large range of variations, but depending on the shape of the velocity profile. So now that we've obtained the 1D blood flow equations, we need to plug in the wall model for the pressure. And in doing so, we finally obtain the 1D blood flow equation in a single artery, where you see here that here we have a nonlinear term that depends on the elasticity of the artery. We have another nonlinear term that characterizes a fluid inertia, and then we have a viscous term and a viscoelastic term. And here we basically have three parameters to estimate in each artery, which is the elasticity of the artery, the friction coefficient, and the viscoelastic coefficient. So in order to see if these equations actually are able to represent a 1D blood flow in a single artery, we did an in vitro experiment with our collaborators from the University of Doshisha in Japan, where they had this experimental setup where a pump would inject a pulse into a straight closed viscoelastic tube, and they would measure. So typically here we would measure here the pressure in the tube over time. And so we did a similar experiment numerically, because here this is a very simple setup that you can do with 1D blood flow equations. And by evaluating the different coefficients of our model, we were able to exactly obtain the experimental results. So this shows that the 1D equations are indeed able to represent average behavior in a straight viscoelastic tube. So now if we want to extend the 1D equations to a network, we have to deal with what happens at bifurcations. So here again, remember that 1D equations characterize behavior in large arteries where the flow is pulsatile and relatively inertial. And so the network here is organized as a parent artery gives rise to two daughter arteries. That's the typical bifurcation you're going to see in large artery networks. And so here, to correctly capture what happens at the bifurcation, we just use these simple boundary conditions, which is conservation of mass and continuity of pressure. And the important thing to note is that these boundary conditions allow you to capture wave propagation and reflection, which, as we said in the beginning, is an essential characteristic that your numerical model needs to have in order to properly describe wave morphology. Because the wave morphology that you can measure, for example, in the right arm, is directly linked to wave reflection and transmission occurring in your network. So now if we combine the 1D blood flow equation with these bifurcation boundary conditions, we tried to see if we were able to reproduce blood flow in a small network. So again, here with a collaborator in the University of Doshisha, we did an in vitro validation on a small network of the same viscoelastic tubes as we used in the previous experiment. So here, this is a network, I think, of 7 arteries or 9 arteries, and we measure the pressure here in the neck. And we see that, again, by correctly choosing the different parameters of each vessel that constitute the network, we're able to reproduce the experimental results, which are in black, and our numerical results here are in green. So here, so here, the conclusion is that we were able, using 1D blood flow equation and bifurcation boundary conditions, to model blood flow in a healthy network. But the thing is that we're usually interested in networks that are unhealthy, and unhealthy networks are typically characterized by vessels that have properties that vary with their length. So typically, the elasticity will vary with length, so the vessel may become stiffer, or the radius may change with the length. So as the vessel, for example, if the vessel has a constriction, the vessel length, the vessel radius, sorry, might change with the length. So when you're using 1D blood flow equation in these pathological networks, it's important to properly solve blood flow equation in vessels that have varying mechanical properties. And so if you go back to how you derive the 1D blood flow equation, you notice that if you now assume that the radius at rest and the elasticity of the artery vary with the distance, an extra term is added into the 1D blood flow equation, which we call a topographic term, which is very similar to the topographic term introduced in shallow water equations when you have your bottom that varies with the position. And so the problem with this term is that it's non-conservative. So when you try to define a finite volume approximation of it, it's not possible to write it as a flux. And so here we use the hydrodynamic reconstruction technique inspired from shallow water equations in order to properly treat the term. And here I insist on this fact because the states that are preserved by the reconstructed state preserve the bifurcation boundary condition or the equilibrium equations. And this means that using a hydrostatic reconstruction technique will actually allow you to properly capture wave propagation and reflection induced by the variable properties in the vessel. So this is again important if you want to infer correct information by analyzing wave morphology. You need to correctly capture wave propagation and reflection. So now that we have a method that is able to describe blood flow in a healthy and diseased network, we looked into an application of our method. So here we consider a network of large arteries, and here there are 55 large arteries. And we solve the propagation of the pressure pulse over one cardiac cycle. So here you have the healthy patient. So then we introduced a disease. We introduced a disease in this patient, which is an occlusion here in the left leg. And this is a pretty severe occlusion because 90% of the vessel is now occluded. And you notice that over one cardiac cycle, you see that the pressure variation downstream of this occlusion is much less important than before, which is characteristic of a very low blood flow going through this leg. And so typically how doctors would treat this pathology is they would introduce a stent in this artery in order to re-expand the vessel and allow blood to flow downstream of the occlusion. However, some patients are too weak to sustain this invasive surgery, and what people do is they use an extracorporeal tube to connect a healthy part of their network to the part of the network downstream of the occlusion in the hopes of restoring blood flow in the diseased leg. And so this is what we did. And we see in here, this is an example how you can use one-dimensional models in order to calibrate the properties of this vessel. Because of course, depending on how you choose the properties of your extracorporeal vessels, you may or may not properly restore blood flow downstream of the occlusion. And here we did a little parameter analysis, and we showed that you could find an optimal set of parameters that allow you to properly restore blood flow below the disease segment while not perturbing too much blood flow in the rest of the body. And what we realized is that the parameters that we found were actually the parameters of the vessel that is used by clinicians when they do this type of surgery. Okay, so now I'd like to talk about when you're studying, when you're looking at, for example, a disease patient like this, we introduce an occlusion here. And so this means that we introduce a variation of the properties of the vessel in this pathology. And here I'd like to talk about the fact that 1D vessel, 1D blood flow equation are not the best to solve the characters features that occur in such a disease vessel. So here we, for example, we consider a stenosis, so a vessel that has a local reduction of its radius. So here we have a 40% reduction. And we compare the wall shear stress and the pressure drop between a reference solution, which is a solution of the long wave Navi-Stokes equation, to the 1D equation, where we set the friction coefficient to 8 pi nu, which corresponds to a Poiseuille velocity profile throughout the whole artery. And we see that we cannot accurately capture neither the wall shear stress or the pressure drop when the 1D blood flow equation. And this is, of course, due to the fact that as when we integrate the RNSP equations and we obtain the 1D equations, we have to make an assumption on the velocity profile in the artery. So in order to overcome this limitation of the 1D equations, we went back to the RNSP equation and decided to, instead of integrating over the whole cross-sectional area of the artery, we're going to divide the artery radius into different rings and then integrate the RNSP equations over each ring. And doing so, we obtain a 2D system of equation that describes blood flow and radius variation in each ring. And that is very similar to the 1D equation. So in the sense that you can plug in the wall model that we derived previously into the same, into this system. And so if we solve this now, this 2D system of equation, where we no longer have to do an approximation of the profile of the velocity profile over the whole radius of the artery, and we go back to the configuration described before, we see that in a similar configuration, solving the 2D equation allows us to recover the reference solution without any velocity profile parameter adjustment. So when thinking about using 1D model in a network of arteries, it might be useful to use this 2D model, which is a natural extension of the 1D model, and to model a pathological network to get a better estimate of the pressure drop and wall shear stress in these disease segments. And so this is just a final slide on the how you can use a final slide on the performances of the 2D model. So it allows you to solve the velocity profile. So here you see that there's a time evolution of the velocity profile in each cross section. And you can also describe variation of the radius of the artery. And these variation can be arbitrarily large. So here, because the equations are dominantly hyperbolic, you see that if I introduce too large variation of the radius, you have a sort of a shock that starts forming. And of course, this situation does not occur in real life. This is just a simulation. So this concludes my first part of my presentation on 1D model and their extension to 2D that can be used to get average behaviors in large arteries. And especially, we've shown that they're able to capture wave propagation, wall deformation to a satisfying degree of accuracy. But sometimes you need to have more accurate results. So I'm thinking in particular when you inject a drug in the cardiovascular system and that drug interacts with the red blood cells, you need to be able to understand how a drug is influenced by the presence of red blood cell around it, and for that you need a 3D numerical solvers. So in this second part of the presentation, I'm going to talk in the time I have left on the Cartesian embedded boundary method for moving rigid bodies for incompressible flows that I've implemented and that Stéphane also has implemented in Basilisk. So just to put things into context, so we need a method that can account for boundaries of arbitrary shape. So typically the geometry of a network, but that is also high order and compatible with mesh adaptation, because the domain length that we're going to try to solve things in is pretty big. And this means that you have to have a method that is efficient, that allows for mesh adaptation in order to reduce computational cost. And this is also true when you're focusing more on particle flows and you want to solve, for example, a flow of red blood cell in a network of capillaries. You again want to reduce the computational cost using higher order method and mesh adaptation. And so we implement this in Basilis in order to use the already existing mesh adaptation framework that Stéphane Popinet has implemented. And so the principle of the Cartesian boundary method is this one. So if this is the solid that's embedded in the fluid, you let the boundary of the solid cut cells. So here we have a grid, and in order to form irregular control volumes. And when you're solving your equations using a finite volume approach, instead of integrating the equations over the Cartesian cell, you're going to integrate your equation over this irregular control volume. And this method works and is compatible with the level set description of the geometry. So here we have a level set that describes the position of the geometry at every time. So how does it work? So in each cell that is cut by the boundary, we use a piecewise linear approximation of the boundary, which is characterized by a normal and an intercept. And we compute these values based on the level set function that describes our geometry, okay? And the level set is sampled at the vertices of the Cartesian cell. And then from these geometrical properties of the intersection of the boundary and the cell, we can determine the volume of fluid quantities, which and these volume of fluid quantities are the volume fraction of fluid within the cell. So this is the white region represented here, and which I named C, and the area fraction, which characterizes the amount of fluid on each face of the cell. Okay, and so using these volume of fluid quantities, we can then write a conservative discretization of a divergence operator, which is the essential operator that you use to solve the Navi-Stokes equation. And here you see that we introduce a volume-weighted discretization of the flux, and that each flux is weighted by the amount of fluid that is present on the face, and that you also have to account for the flux on the embedded boundary. So here, when you discretize the divergence, you account for this flux weighted by the area fraction, this flux, this flux, this flux weighted by the area fraction, and this flux weighted by the embedded area fraction. And so here, the principal difficulty is going to be to compute the flux on the embedded boundary. And so to do so there are two cases. If you provide a Neumann boundary condition for the quantity you're trying to compute the flux of on the embedded boundary, then the gradient of this quantity is already the Neumann boundary condition. If you however provide a Dirichlet boundary condition, and your flux involves the gradient of that quantity, then you have to use a more sophisticated method to evaluate the flux. And here we use what Johansson and Kolela did in their paper in 1998, and that was extended by Schwartz and Kolela in 2006, where we basically compute the gradient normal to the boundary using an interpolation along the direction of the normal, and we compute the values S1 and S2 used in these interpolation using a quadratic approximation along the direction orthogonal to the principal direction of the normal to the embedded boundary. So this allows us to have a higher order approximation of the gradient at the boundary, and therefore have a higher order discretization of the divergence of the flux. So when you're looking, so the second feature that is important to take into account when you're using embedded boundary is when you're solving a conservative equation. And if you use the divergence of the flux that I defined here, you notice that it's weighted by 1 over the volume fraction times the phase fractions. So if you use just this conservative discretization of the divergence, you get a CFL condition on your explicit scheme that is weighted by the volume fraction and the phase fraction, which can be arbitrarily small. This means that this would lead to an arbitrary small time step, which is not favorable for efficient computations. So to avoid this a small cell CFL, that's what we call it, we use a flux redistribution technique where we basically compute two discretizations of the divergence, the conservative one that I presented before, and a non-conservative one that doesn't account for volume or area fraction. And then we do an interpolation between those two conservative and non-conservative divergence. And then we redistribute the excess flux to neighboring cells in order to always have, in the end, exactly this that is added to the local cell. So here I just want to note that in the case of a moving boundary, you also have to account for the fact that the control volume in the cell is changing, and we introduce this extra term in order to account for this. So now that all the different techniques that are involved with Cartesian and boundary method are defined, we can extend this. They were defined for a uniform grid. We can extend this to a quad Artery grid in Basilisk. And so to do so, we use prolongation and restriction operators. And I won't go into too much detail since I don't have too much time left. But the idea is that Basilisk allows you to, wherever you are in the domain, whether you're on a uniform grid or an adaptive grid, that if you're in this cell, you always have access to a local stencil that has this at the same level as the cell you're in. And so in the case of this cell, this means that we have to introduce fictitious cell, which we call hollow cells, and we have to update the values in these cells using a prolongation operator. And for example, if you're looking at this cell at a lower level, then you need this fictitious value that you compute using a restriction, using the values at a higher level. So I won't go into too much detail, but this works very well, and this means that you can implement the embedded matter method both on a uniform grid and a quad Artery grid with exactly the same, because each cell has access to a local stencil. So now we can use this embedded boundary method to solve the incompressible Navi-Stokes equation with the following boundary conditions. You assume that the velocity is equal to the particle velocity, the boundary velocity, and that the pressure gradient on the boundary is 0. And we solve it using a fractional step projection method that's been described by Stefan in several articles, where you first solve the nonlinear advection, you then solve the viscous stresses, then you project the pressure in order to render the flow incompressible. And now I'm going to show several examples of several validation examples for both fixed and moving boundaries, where we use the embedded boundary method. So here, this is an example taken from Johansson and Kodela, where we solve this Poisson equation on a complex geometry, and we have an analytical solution for for this problem. And so we can compute the error, and we see that as we increase the number of cells, or as we reduce the mesh size, we obtain a second or almost third order convergence for the error. So this is due to the fact that we do a high order interpolation of the gradient at the boundary of the domain. Then we can also look at lubrication problem, where we put a sphere near a wall. The sphere doesn't move but has a velocity u, and we look and we compute. We let the problem run, and we compute so this is we solve the Stokes equation in this case, and we compute the normal force acting on the sphere, which we compare to the Stokes drag, and depending on the gap width, we have an analytic formula for the normal force. So here, this is a representation of what we can do with Basilisk using two different gap widths. So here, this is the larger gap, this is the smaller gap. And we see that here, the mesh adaptation works really well because the mesh is at its finest in the gap, where most of the flow feature happen. And further away from the gap, you see that the mesh size reduces, even along the boundary. So here, this shows that you don't even have to have a uniform grid size all around the boundary. The embedded boundary method allows you to have variable grid size to describe the geometry of your domain. And here, if we compare the normal force to the analytic formula for different gap length, we see that we have a very good match with the analytic formula. Another example that we can look at here in the more inertial regime is the starting flow behind a fixed cylinder at Reynolds 1000. So here in this video, on the bottom, you see the mesh levels. So again, you see here features of the mesh adaptivity, where in regions of large variations of vorticity, we use a fine mesh size, whereas further away, we use a much coarser mesh size. This allows us to reduce the computational costs, all the while correctly capturing the correct, so drag. Here, the drag is represented in green, and is compared to results from the literature. And we also see the pressure drag and the viscous drag here. So this problem is interesting because we can do here, the cylinder is fixed and the flow is moving around it. But if you change the referential, you can make the cylinder move and fix the flow around it. And this is also a great validation case for our moving boundary approach using the embedded boundary method. And so here, this is exactly the same setup, but instead of moving the flow, we move the solid. And again, we compare our results obtained with the moving cylinder to the results obtained with the fixed cylinder. And so we see that the viscous stress is correctly matched, but here the pressure stress has the right amplitude, but much more oscillations. And this is due to the propagation of errors in the projection method through time. And this is especially important for moving boundary problems. So these oscillations reduce as you increase the number of cells in the domain, or you can use something that's called double projection, which I won't detail here, but it's the idea basically is to, instead of projecting the velocity, you project only the history of the velocity, which doesn't include noise errors from the previous divergence, and allows you to reduce the amplitude of the oscillations. So this has been done by Stéphane Popinet for fixed embedded boundaries, and we're now trying to extend this double projection method to moving boundary problems. And the only difficulty lies in what boundary conditions you need to apply for pressure in the double projection method in the case of a moving object. And so just to wrap up, here are some other validation cases for moving boundary problems. So here we have a settling sphere in a large domain at Reynolds 360, and we compare our results to literature, and we see that we capture the correct cycling velocity. And the last example I'd like to show is a cylinder settling in a confined environment. So here, both the walls and the cylinder are solved with the embedded boundary method, and we see that we obtain the right behavior at longer times. However, for the initial state, we don't get this overshoot, which I don't really know why. But the final Reynolds number and the final settling velocity is the same as the results we compare it to. So I don't really understand why we don't capture this transient phenomenon at the beginning. So to conclude this presentation, I have talked today about the efforts that can be done to model blood flow in the cardiovascular system. And I think what I want people to understand is that my opinion is that you do not need to solve the 3D Navier-Stokes equation in the entire cardiovascular system, and that depending on which domain of the cardiovascular system you're interested in solving, you need to choose the appropriate model depending on your needs. So today I have shown that for the large arteries, you can use a simplified one-dimensional models which solve for pressure and flow rate, and that gives you very good results that can be useful for clinicians. And of course, these models are very efficient and can almost give real-time data to clinicians. And then as you move along the cardiovascular network and you notice that the amplitude of the pressure oscillations lower and lower, you can use a simpler and simpler models. So you can use zero-dimensional model, which are basically the one-dimensional model integrated over the length of the domain and correspond to an electrical analogy. And finally, as you reach the capillary mesh, you can use, instead of solving blood flow in a network, because the capillary are tri-connected and form a space-filling mesh, you can apply a homogenization technique and solve for only the equivalent properties of the corresponding porous media. So the goal now would be to connect all these models together and to be able to dynamically choose, depending on some sort of a model estimation error, which model is best to use depending in your cardiovascular system, depending on computational constraint and the degree of accuracy that you want and what variables you want to be able to predict. Thank you for your attention. So please feel free to ask questions.
décisions jeunes et
Okay, thank you, Arthur. Des questions?
Moi, j'ai une question.
Oui,
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 salut,
Stéphane.
désolé, j'ai raté la première partie.
Oui.
Je suis un peu arrivé au milieu, donc je vais peut-être poser une question qui est à côté de la plaque. Mais quand tu as parlé des modèles réduits,
Oui.
réduites,